Hi, and welcome to USMA Orgo. We're now at Chapter 10, talking about radical reactions. So the big things to start off with is understanding what radicals are, and then how do we produce radicals. And usually when you have heat or some kind of light, which is represented by the H nu there, that you're going to get some sort of radical reaction where you're going to get a single electron generated on a species. Once we do that, you have to understand the stability of radicals. That way you can predict the outcome of a reaction. As you know and you have heard, radicals are very important in life and in our bodies. You've probably heard about free radicals and how they damage things in the body. So they're important to understand, and then also taking advantage of the chemistry, we can also use that to fix some of those problems that we have with free radicals. So one of the first mechanisms to understand is this radical chlorination mechanism. So in general, you're going to have three steps, which are over here, for a radical reaction. Initiation step, which in this case is this first step right here, where you create a radical. Notice you have heat or light. And then you have a propagation step. Usually that's two steps. These are the two steps where you start with a hydrogen abstraction, and then you create another radical. And then once they create that radical, that can react with another species to create a product and another radical, which can keep going until it gets terminated. And this is one example of a termination step here, where you have a radical chlorine and a radical methane. They react together, and now at the end you have no more radicals. So your book goes into radical methane, but radical chlorination of methane, but it also talks about ethane and higher alkanes. So take a look at that and see how that's different with higher alkanes. Another thing to note is that chlorination is very unselective. So you may get multiple spots chlorinated, or you might get multiple chlorines, because the radical is very reactive. And then also, when you talk about bromine, then bromine is a little bit less reactive, but it's more selective. So you can specify, or at least predict, where you think it's going to go. There's also this idea of when you create a radical, you can create a tetrahedral chiral center. So here the molecule has no chiral centers, but because we create the radical, we now have the ability to put the next radical attachment on either side, which gives us, in this case, an S or an R configuration around that chirality center. So that's important to understand. And then if you go with something a little bit higher that has a chiral center already, now the next addition can give you some diastereomers or many different combinations of chiral centers as you go through. So other things to take a look at is this allylic halogenation. So understanding how reactive allylic position is, and same thing with benzylic substitution. Both of those are kind of unique ways of reacting something to a position next to a double bond rather than across a double bond like we've been doing. This is only possible with radicals. And then finally in the middle there, I have NBS. There's several different types of these types of succinimides that allow us to add bromine or chlorine in a fashion just like a radical you would, but it's a little bit more easy to work with when you're doing actual synthetic work. So the last thing to talk about here is radical addition of hydrogen bromide. So this is anti-Markovnikov addition. So this is something that we can use to specify if we need an anti-Markovnikov product. So we use the radical. Now the important thing to pay attention to is we need some sort of radical initiation, which in this case is a peroxide. So one thing I'll tell you as you go on further through the course, anytime you see a peroxide, something weird is going to happen. And in this case, what I mean is you're going to get an anti-Markovnikov addition rather than a straight Markovnikov addition. So you can walk through the process, same as what we kind of saw before, but you have the double bond here now. But in the end, we get the bromine on the outside, which is one you would not predict. So that's why it's an anti-Markovnikov product. That's it for today. See you in class. Take care.